Welcome to my talk. My name is Bari. I'm a physics master's student at Brown University. Today I'm going to be discussing a satellite proposal that Brown and Columbia University are developing to capture the first video of a black hole. I'm going to make that statement technical and precise in a few slides. But essentially what we're developing is a VLBI radio telescope in low Earth orbit that will observe black holes at 86 gigahertz. At any point during the talk, please feel free to interrupt me with any questions, any objections, and strong skepticisms. So this is the basic principle behind the satellite proposal we're developing. This Pathfinder satellite will be operating in low Earth orbit, just about 400 kilometers from the surface of the Earth. And the key idea is that low Earth orbit gives you the time resolution, the temporal resolution required to resolve the accretion disk of Sagittarius A star. Why? That will hopefully become clear in a few slides. But the essential idea is that we will be co-observing black hole targets with another radio telescope known as the Black Hole Explorer satellite, which is a proposal being developed by Harvard and the Japanese Space Agency. And the idea is that we would correlate our radio signals on the ground with the Event Horizon telescopes and combine our radio signals to get a clear video of the black hole. So when I say video of a black hole, let's make this more precise. What time scales am I talking about here? Well, if we look at Sagittarius A star, the black hole at the center of our Milky Way, the orbital period of Sagittarius A's accretion disk is on the order of 30 minutes. Now, what exactly it is, we don't know, because the spin of Sagittarius A is not well constrained. Its mass is well constrained, but spin is much more difficult to constrain. You can make preliminary measurements on the spin based on the bending of light and polarization of light near the black hole, but the constraints on the spin are not as well defined as the constraints on mass for Sagittarius A star. So the essential idea is that if you'd like to time resolve this accretion disk, you need to be taking pictures of the accretion disk on sub-ISCO timescales. So you need to be capturing an image of the black hole on less than 30-minute timescales. And a low Earth orbit, it seems, affords us the temporal resolution required to resolve the accretion disk. According to some of the preliminary results that I'm going to show today, with a low Earth orbit VLBI satellite, you can capture an image of Sagittarius A star once every 22 minutes or so, which is below the sub-ISCO time requirement. I'm going to be getting into all of this in a moment, but the end result, once you have a video, what do I mean by video? What I mean is you've got several pictures of the black hole's accretion disk evolving in time, and once you stack those pictures up, you can trace the evolution of the hotspots in the accretion disk over time. And so these results are not for Sagittarius A star. This is for M87. So that's why the temporal resolution required is much, the requirement is not as stringent. M87's accretion disk has an orbital period about 1,000 times longer than Sagittarius A star. That's because it's simply a much bigger black hole. It's a billion mass solar mass black hole instead of a million solar mass black hole. And so if you'd like to create a video of M87, the requirements in terms of temporal resolution are not as strict as for Sagittarius A star. So creating a video of M87 can be done with a telescope, a radio telescope that's in medium Earth orbit. But for Sagittarius A, this is not the case because the orbital timescale is much shorter. And so that's where this low Earth orbit satellite comes in. So before I show all the results today, I'd like to thank some of the collaborators that we've been working with. Our advisors are Suvi Gazari, Crystalline Smith, Travis Fisher, Luke Anderson, Rick Fleeter, Ben Hudson, and some of the the Pathfinder team at Brown University and Columbia. Some of the folks here are Graham, Mia, Sebastian, who's here, Ariel, who has, oh, she's not here yet, but she's the reason I'm here and not still in Brown. Yeah, we drove, I had to wake up at 5 a.m. today, believe it or not, to be here. But yeah, so all of the work is in collaboration with these folks. So this presentation is a bit long. You won't remember much of it, but if there's three things that you should take away, it's these three things. So Our primary science objective is to temporally resolve the accretion disk of Sagittarius A star at 86 gigahertz. How are we going to do that? Well, we're going to be putting a satellite in low Earth orbit. The proposal is to put a satellite in low Earth orbit that can temporally resolve the Sagittarius A star due to its rapid orbital period. And the way it's going to do that is by correlating its interferometric fringes with ground telescopes that are part of the Event Horizon Telescope collaboration. So the three key points to take away from this talk is that to capture a time-resolved video of Sagittarius A star, we'll be combining a VLBI platform with a low Earth orbit satellite to get the temporal resolution required, which is sub-ISCO timescales to resolve Sagittarius A star. So this is the entire talk in a single slide, if you'd like to. Yes, please.
Which is VLBI already exists, and of course you can take snapshots of it. Why is that not good?
So VLBI certainly does already exist, and that's how the Event Horizon Telescope captured the first image of M87 in 2019. But the problem is that on Earth, the principle behind combining the radio signals between different telescopes depends on Earth rotation aperture synthesis. So you need to wait for the rotation of the Earth to happen so that you can cover up the UV plane. You can cover up the Fourier domain of these black hole targets. So the temporal resolution of the EHT telescopes is limited by the rotational period of the Earth. So that's the primary restriction. So when you see, I'm going to show in a couple of slides, but when you see the first image of Sagittarius A star taken by EHT, that's an average over 6 days of observing a Sagittarius A star with 5 telescopes from the ground. So you won't be able to track the hot spots, in other words. But for M87, it's different. For M87, you have less stringent timescales. But that's why it's not possible to access the temporal resolution required from the ground. Yeah.
I mean, you do have some information. You have some points in the UV plane, but you're right. It's limited. You can't make it.
That's right. And the end goal is that you'd like to fill up the UV plane as much as possible. But with ground telescopes, the first thing is the Event Horizon Telescope functions at 230 gigahertz. So our telescope will be functioning at 86 gigahertz, which would fill in more of this inner core of the UV plane, which would give you more information about the accretion disk and larger scale features around the black hole, as opposed to EHT. Yeah. Cool. That being said, I just like to preface this by saying that it's not all sunshine and roses when it comes to a low Earth orbit telescope. The whole reason that this has not already been done is, first of all, it's very hard to send down a lot of data generated by VLBI from space down to the Earth. This is the key technological capability that has changed in the last 10 years, the ability to send gigabits of data down from low Earth orbit to the Earth. That could make a mission like this possible only today. But the other problem, there are several problems, very technical challenges with a low Earth orbit. First of all, you're closer to the Earth. So thermal emissions, infrared emissions from the Earth are larger than for a satellite that has lower temporal resolution, but greater angular resolution out in medium Earth orbit. But also, because you're moving so fast, your temporal resolution might be fine. But there's a problem, which is that you need to rotate your antenna very quickly to look at the same thing. So the key trade-off is that as you increase your orbital altitude from the Earth, your angular resolution increases because your longest baseline increases, but your temporal resolution decreases because your orbital period increases. So that's the trade-off that we're making here. Yeah, please.
Yeah, so this is this picture on the top right.
Yeah, I'm going to zoom in on that. Yeah.
So if I remember correctly, the Fourier coefficients sample are like go as the baseline. It seems like all these long baselines are kind of sort of more or less aligned in the same direction. Is that a problem?
Yeah, so ideally you would like a wide diversity of alignments between your baselines on the Earth. I'm not an expert on the baseline alignments of the EHT, but after they added ALMA certainly and the GMVA, which also operates at 86 gigahertz, they had many different orientations for their baseline lens. So as I'll show in a few slides, horizontal baselines and vertical baselines can give you different kinds of information about the diameter of the black hole target and the spin of the black hole target. So ideally, you would like to have as many different kinds of alignments as possible with your baseline. But yeah.
Yeah, questions are just a question. The nation with this smaller satellite have, will it be rotating on the same plane as the bigger one? Or?
So that's a great question. So this satellite would be in low Earth orbit with a circular orbit, very close to zero eccentricity. And it would have an inclination that would be above about 78 degrees. Now, why is that? It turns out that at higher latitudes, the amount of data you can send down, your ground coverage is higher at higher latitudes. So that's one reason why we selected higher latitudes above 78 degrees for our orbital inclination. But that also impacts your angle of elevation with respect to the target. These are simulations we have not run yet, but for the time being, our inclination would be above 78. Yeah.
Another small question: what kind of hardware is going to be on this small satellite? Are you going to have the entire hydrogen time standard population, or is it going to be like just super fast data transfer and transfer related this way, accounting for every single possible?
So let me understand the question. So are you asking if we're going to be using hydrogen masers for
Yes,
correlating
I
the signal?
Russians use when they're radio astronomy. They carry like the entire like time standard to do precise time correlation. How will you fit this one in smaller satellite?
Oh, that's a really good question. So as I'll show, maybe I can actually jump to this since you raised it. Yeah, but this is the exact answer to your question. So if you to perform very long baseline interferometry, you need to know exactly when your radio signals are hitting your antenna. So you need a very precise atomic clock. Hydrogen masers are too heavy to put on a small satellite. As I'll show in a few minutes, this is a small satellite only in name. It'll become clear what the swap requirements are. This satellite would be about 100 kilograms in weight, 500 watts in power, and about $25 million in cost. But the ultra-stable oscillator that we tentatively are looking at is the oscillator that flew on the JUICE mission for the European Space Agency, and the USO being developed for NASA and ESA's LISA mission. So both of these would satisfy two constraints that you need for ultra-stable oscillators. One is that you need less than 1% phase error in your signal, and one is that you need less than 10% coherence loss in your signal. And so these are the tentative oscillators that we're looking at. But basically, LISA's oscillator would do the job, which is currently under development. But yeah. Yeah.
I've read your proposal. Thank you for saying it. That really what's driving the choice of 86 gigahertz versus higher frequency 345 that PHX has. Really that, rather than filling in the short baselines, you can't achieve the coherence that you need.
So the short answer is no. The reason why we selected 86 gigahertz is for several reasons, but the main reason is feasibility and cost. So if you operate at 345 gigahertz, several things happen. First of all, your antenna is much more sensitive to higher frequencies. So that means any small surface error, any error greater than about 40 RMS, 40 micrometers for your antenna would mean that you suffer more than 1 degree phase error in your signal. So at higher frequencies, you have to have a better antenna, and you have to cool down the antenna to sub 15 degree Kelvin temperatures.
Why is that? The temperature affects the noise that enters directly in the noise of Earth.
That's right.
It's only the quantum noise.
That's right. So the reason why, so let me just come in over here. So here's where the observing frequency makes a direct difference. Oh, maybe you don't see it in this slide. Okay. But so if you observe at 345 gigahertz, First of all, you need a better clock. You need a better atomic clock.
Okay, that was my question.
Yes. So because your phase error would be greater at higher frequencies.
Can't afford to use it.
That's right. That's right. Also, at 345 gigahertz, you would be examining more horizon scale features of the black hole as opposed to more larger scale structures like the accretion disk or jets. So yeah.
If
Does
you
that
could
make
solve
sense?
it, you could make portable dish. I guess the PHEX people think they could do.
Mhm.
Could you afford to have two receivers? Or have you one at 86 and one at
Yeah. So the Bex team has a dual frequency receiver system, and they need it for making sure their higher frequency measurements are uh, they're using frequency phase transfer so that their lower frequency measurements are essentially a ruler they can use to calibrate their higher frequency measurements at 345. Now, for our satellite, as I'll show in a moment, adding a dual frequency system makes the internal design of the satellite much more complicated. It exceeds the size, weight, and power requirements for our NASA Pioneers program mission. So what the kind of trade-off we've made is that we will be only observing at 86 gigahertz, not higher frequencies. Yeah,
This is the end of the good. Okay.
yeah. So essentially, the short answer is feasibility. To make the mission more feasible, we're observing at a frequency 3 times less than Bex. Now that raises a problem, right? Because the Event Horizon Telescope only operates at 230 gigahertz. So that raises a major problem, which is how do you correlate your radio signals with ground telescopes if EHC is only at 230? And so right now the answer we're looking into is the future. Essentially, by the time that NGEHT, Next Generation Event Horizon Telescope, is operational, in about a decade, it should support both 86 and 345 gigahertz observations, so it can do multi-wavelength. That's one scenario. The other thing is GMVA, the global millimeter VLBI array that consists of the Green Bank telescope or Haystack, already has 86 gigahertz supporting observatories. So the problem of 86 gigahertz is, at least tentatively, that we have a few supporting ground stations that do observe at 86, and hopefully more when NGEHG becomes operational in about a decade.
There's also been a lot of progress being made in compact clocks, optical clocks. Lincoln Labs people hoping to do something that's sort of a meter size.
We should let him get on to it. We're asking all the questions.
No, but this is, actually,
I mean,
well,
you're talking about a 10-year horizon,
yeah,
waiting for 86. That time feels like
right. Yeah, by that time, Lisa's USO should be ready, for instance, which is much better than the 2 orders of magnitude better than current USOs. But yeah. Okay, good. So let's see. So that's a key takeaway of the talk, but now I'm gonna really dive into things. So first of all, just briefly, the spaceflight heritage for Brown University consists of three satellites, which were all CubeSats developed under NASA's CubeSat launch initiative. Chandler Stevenson actually led the development of PVDX here, which will fly, I believe, next year, possibly, if funding survives. And so about 7 or 8 months ago, we were soliciting proposals for what the next satellite mission would be. And that's when I raised this idea of a Pathfinder mission, which would have the following primary science objectives: time resolving the accretion disk of Sag-A at 86, but also potentially looking at binary black hole targets, including OJ287, which I'll discuss in a few slides, potentially enabling multi-messenger astronomy by time resolving the jets from a binary system such as OJ287 at the same time as a gravitational wave observatory captures the gravitational wave signals from this. And finally, our last secondary science objective is to conduct an 86 gigahertz survey of the night sky using VLBI, looking at quasars and blazars and other high flux density targets. This is the main science traceability matrix for our telescope. This is too much text for one slide, but the key takeaway is our three main science objectives, which is to understand black hole formation, specifically by constraining the mass, spin, and luminosity of Sag-A and M87, to look at binary black hole targets at 86 gigahertz, specifically OJ287. I'll discuss why we're so focused on OJ287 in a minute. It turns out that OJ287 has an optical outburst every 12 or so years. And the next optical outburst around 2033 is predicted to occur when our satellite would be operational in LEO. And the final primary science objective would be to understand accretion flow dynamics by conducting essentially a population study on quasars and blazar targets. But this is all too much text. This is just to illustrate our PSOs. So now, just to make sure that everyone is on the same page, and because it's instrumental to how we hope to capture the first video, the first time results video of Sag-A's accretion disk, I'm going to briefly discuss how EHT captured the first image of M87 and Sag-A. So if this plays, the first ever video of the first ever image of a black hole was M87, a black hole 55 million light years away in the constellation Virgo. And if you zoom in to this constellation a little bit faster, maybe, then you will see this this giant galaxy in the optical regime. If you look a little bit in the radio, you'll see the fade of a jet coming out of the active galactic nuclei. You keep zooming in, keep reducing your angular resolution, the jet becomes prominent, and ultimately at 230 gigahertz, you see the supermassive black hole at the center of M87. This is a billion solar mass black hole, and this was behind the first ever image of a black hole. And so looking at a multi-wavelength picture of M87, this is what we see at low frequencies. But as we go from, I don't know what the exact frequency here is, but as we go from about 86 to 230 gigahertz, the optical depth of the jet and the accretion disk slowly reduces, and you're ultimately left with the black hole shadow at 230 gigahertz. And the second famous image of a black hole was, of course, Sagittarius A star. Andrea Ghez and her team at UCLA are famous for putting constraints on the mass of Sag-A by looking at the orbits of stars near the center of the Milky Way. The closest that any of these stars get to Sag-A is about 1,000 times the Schwarzschild radius of Sag-A. So despite the fact that they're quite far from the supermassive black hole, you can clearly see how much of an effect the black hole has on their trajectories. And so all of these, both of these images were taken using VLBI, which is a process of combining radio signals from multiple different radio antennas by correlating their signals and seeing exactly when these radio signals hit each antenna. Now, I'm going to make this more precise in a moment. This is the big picture behind capturing an image of a black hole. You need to use radio telescopes. You cannot use optical telescopes. VLBI does not work with optical telescopes. It's very hard, for reasons that I'm not an expert on, very hard to correlate the precise time of arrivals for optical wavelength photons as opposed to radio wavelength. And so using radio telescopes operating at 230 gigahertz, the EHT samples the black hole in the Fourier domain on the UV plane. And the better you can sample the black hole on this UV plane, once you implement the inverse Fourier transform, the better your reconstructed image of the black hole target. And so ideally, if you filled up the Earth with radio telescopes all around the world, of course, we're all laughing because NSF, but then you would get perfect coverage of the UV domain. You'd get perfect coverage of the UV plane. In reality, if you have just two telescopes, for instance, of course, if you have just one telescope, then you can't correlate any signals. What each telescope is measuring is the electric field intensity near these black hole targets. And so this UV plane is just a Fourier transform of these electric field intensities, as I'll show in a moment. But each pair of telescopes defines a unique baseline vector on this UV plane. And because this UV plane is symmetric, each point also samples its opposite partner across the plane. And so exactly as you're mentioning, how does the EHT create a picture from such a sparse set of data? Well, one of the things that they can do is wait for the Earth to rotate. As the Earth rotates, the projected distance between each of these telescopes, the projected length of each of these baselines, creates these UV tracks on the Fourier domain, slowly filling up the Fourier domain. And so over 6 days of observing Sagittarius A, oh, actually this is M87, you get something like this. As you cover up the UV plane better and better, the reconstructed image improves better and better. Let's see if this restarts. You can see at first it'll seem to be 2 horizons, but of course that's not physical. And as the UV coverage improves, you'll see one event horizon and the black hole shadow begin to emerge. So this is the practice of Earth rotation aperture synthesis, but it's limited by the orbital period, the rotational period of the Earth. So now I'll briefly discuss the next step with the Event Horizon Telescope, which is a satellite mission being developed by Harvard and the Japanese Space Agency, BEX. Now, for legal reasons, I've been asked to state that we are not affiliated with nor supported by the Black Hole Explorer mission at Harvard or the Event Horizon Telescope. Although once we're further down the line, we have to co-observe black hole targets with them. So the main mission parameters of the Harvard satellite is it's a radio antenna that will essentially fly out to medium Earth orbit, operating at a dual band frequency of 86 and 345 gigahertz. The reason why the Harvard telescope uses a dual band frequency is to perform frequency phase transfer, make sure that their high frequency data their lower frequency data can serve as a kind of ruler for their higher frequency data. This mission is going to last about 2 years, and its primary science objective is right here. The primary science objective of the BEX mission is to improve the angular resolution of the EHT image by an order of magnitude, from 23 microarc seconds to 5 microarc seconds. Now, what do you get from improving the angular resolution by an order of magnitude? What you get is confirmation, ideally, of the existence of the photon ring around a black hole for the first time. The photon ring is the last stable innermost circular orbit that photons can make around a black hole. Do we have any markers here by any chance? Oh, thank you so much. So, for instance, for a Schwarzschild black hole, let's just draw out some of the essential features. For a Schwarzschild black hole, the radius is at r equals 2m. This is where our event horizon is. The photon ring is at r equals 3m. This is the last stable circular orbit for photons. ISCO, the innermost stable circular orbit, is a little bit further out. It's double the distance of the photon ring. And finally, the black hole shadow makes this kind of boomerang trajectory that just grazes the photon ring of the black hole. And so this is the hole that you see when you look at the EHT images. This hole is created by the black hole shadow. So the primary science objective of the BEX mission is to confirm the existence of this n equals 1 photon ring around a black hole. And why is there a primary science objective to do this? Well, by confirming the existence of the photon ring, you can put a constraint on how fast the black hole is spinning. As I'll show in a few slides, the photon ring is much like a dough of pizza. If you start to spin the black hole, if you have a curved black hole, the photon ring becomes more oblate, it becomes a photon shell. And so by measuring the deviation of the photon ring from r equals 3m, you can ideally put a constraint on the spin of a black hole. So that is, this is, by the way, our old name, which I've been asked to change, but I was sleep deprived on the way here, so I didn't have the chance. But now I'm going to briefly, unless there's any questions, I'm going to briefly discuss our primary science objectives. So the goal, oh, sorry, was there a question? Oh, yes, please.
Do they want to use ground stations? Why don't they go 30.
Yeah.
Who else is used 345?
Oh, okay. Yes. So there's a problem with operating at 345 gigahertz as well, which is there's no one on Earth doing 345 gigahertz. And so two things. First of all, it's the same wishful thinking that by the time NGEHT becomes operational in a decade, it would support higher frequency observations. But the caveat is that 345 gigahertz observations can be supported by limited ground stations on the Earth because it depends heavily on atmospheric visibility. So you need to have a high elevation for your ground station sites if you'd like to be observing at 345 gigahertz. So to the best of my understanding, the justification behind the 345 gigahertz is to wait by the time that BECS will launch around 2032 or 33, ground stations that are part of NGEHT would support 345. So now the key question becomes to what degree does adding a second satellite help in low Earth orbit? And the precise answer is right here. So let me take you through what you're seeing in these images. So let me just zoom in on the first plot we have here. So this plot is the UV plane for looking at Sagittarius A star over a period of 30 minutes. So this plot captures the UV coverage using only the Event Horizon telescope operating at 230 gigahertz for a period of 30 minutes. You essentially get a snapshot image of Sagittarius A star with a 20% radio coverage. I'm going to show the reconstructed images in the next slide, but this is what the EHT can capture with Sagittarius A in 30 minutes. The reason why we're using 30 minutes here is that's the time scale of the accretion disk of Sag A. Now you add one telescope in low Earth orbit, that adds significant temporal resolution. And why does it do that? It's because the UV tracks are much more rapid and dense over the same time period. Again, this is 30 minutes with one LEO satellite in addition to EHT, operating at 230 gigahertz, both the satellite and the EHT. And this achieves a UV coverage of 56%. Now, the question is why? And also there's an asterisk mark. Why does adding a LEO satellite help this much? First of all, the rapid and dense UV coverage is because a LEO satellite has a 90-minute orbital period compared to the 24-hour orbital period required for Earth rotation aperture synthesis. So these are the ground stations that are part of EHT, but even adding one LEO satellite has multiple baselines to the 11 EHT stations. So this is what you see in effect. Now, what is the asterisk mark? The asterisk mark is in here, 230 gigahertz. Our satellite will be observing at 86 gigahertz. So why am I not showing 86 gigahertz here? The short, yeah, please.
Those tracks have a finite width. Is that due to the bandwidth? In other words, given geometric baseline, you get multiple via over lambdas. Or is it something else?
So I don't have a good understanding of why these have a finite width. This comes from an algorithm called PRIMO that the Event Horizon Telescope collaboration uses to reconstruct the images. But yeah, maybe there's a better explanation here. It,
It's the bandwidth. You could get the UV coverage just by going to the wider bandwidth.
Right. The problem with wider bandwidths is, well, they're harder, but wider bandwidths also gives you less thermal noise. So they're beneficial in that way too. But for the BECS satellite, they're using a bandwidth of about 32 gigahertz, which is already kind of pushing the limit. But one justification, I don't know, I'm speculating here, is possibly something like something like an uncertainty principle in the Fourier domain here on the UV plane. But I'm uncertain how this algorithm PRIMO works. Yeah. So this is the essential justification for adding a satellite in LEO. We are now doing simulations with co-observations at 86 and 230 gigahertz. The library used to make these simulations did not support multi-wavelength frequency observations until very recently. So that's what we're doing. And if you keep this cycle going, of course, add more satellites in low Earth orbit, of course, your UV coverage improves even more over the same 30-minute time scale. So in terms of reconstructed image quality, this is what we're looking at. If you perform the inverse Fourier transform, first let me just zoom in here. This is what a reconstructed image using just EHT observing for 30 minutes would look like, a 20% UV coverage. It's essentially a more blurry image of the donut 2019 image. But adding a single satellite in low Earth orbit now enables you to track hotspots in the accretion disk of Sagittae once you've achieved 48% radio coverage, UV coverage. And of course, this cycle continues for more and more satellites. So this is the essential benefit in adding a LEO satellite. By tracking these hotspots in the accretion disk over time, you can put a constraint on the spin of Sagittarius A star, and from the spin of Sagittarius A star, you can test whether it's a black hole powering the jets coming out of either M87, or for Sagittarius A star, it's not known if no jet has been observed yet. Yeah. So now I'll briefly discuss the mission parameters for our proposed satellite mission and why we selected a low Earth orbit as our, in addition to temporal resolution. It turns out that low Earth orbit is beneficial for interstellar scattering, among other reasons. But ISM scattering is a major problem when it comes to trying to capture a video of Sagittarius A star. Sagittarius A star is right in the middle of the Milky Way galaxy, and so that means ISM scattering for Sagittarius A star is a factor of 1,000 times worse than M87, which is off the galactic plane. And so ISM scattering is not as much of a problem. Temporal resolution is not as much of a problem for M87. So essentially, M87 is an easier target in many ways than Sagittarius A star, perhaps even a calibration target. So first and foremost, this, do we have...
ISS would be less severe if you went to higher frequency.
That's right. That's right. And so this is something that hurts us at 86 gigahertz. We experience more ISM scattering, but something that works in our favor in terms of ISM scattering, as I'll show in a few slides, is our baseline length with the Earth. ISM scattering also depends on the length of your longest baseline. And so because the BEX satellite is out in medium Earth orbit, about 50 times further than BEX Mini, than Pathfinder, it will suffer less ISM scattering despite the fact that it's operating at a observing frequency 3 times less. Now these are, I have to state, still preliminary calculations. So these are things we're working on right now for ISM scattering. But these are the preliminary swap requirements for our mission. It would be about 100 kilogram satellite, consuming about 500 watts of power, costing about $25 million. And this fits the constraints of a NASA Pioneers program mission. NASA sends small satellite missions up to the International Space Station every 4 or 5 years with a cost cap of $20 million and weight cap of about 100 kilograms. And these are the essential parameters for our proposed satellite mission. The SEFD, this gives you a sense of how powerful this sensitive the telescope is about 32,000 Jansky's. I'll show how that compares with other telescopes in a moment. The thermal noise, usually you would like a thermal noise. Oh, any questions? Oh, yeah. And that's right. SEFD is a little bit like golf. The lower it is, the better your telescope is. I've never really understood golf until I watched a golf game. And I never really understood SEFD until I watched a golf game. And so if you compare the SEFD of our proposed satellite with, for example, BEX, SMA, ALMA, or SMT, first of all, ALMA is the most powerful radio array on the Earth. You can see it has a very small SEFD. The BEX satellite, of course, has much cooler receivers operating at about 4.5 degrees Kelvin. So it makes sense. Their SEFD is about a factor of 2 less than ours. And SMA and SMT both have smaller SEFDs as well. So this gives you an order of magnitude for how sensitive this proposed satellite would be. And in regards to the other mission parameters, the thermal noise, this is with our old defunct name, but the thermal noise on the space baseline is about 12 millijanskis, and on the space ground baseline is about 40 millijanskis. Now, to put this into context, you would usually like a thermal noise less than 10 millijanskis when you're observing a black hole target. Now, the question is, why is the ground thermal noise so much worse than the space thermal noise? And the short answer is that the atmosphere causes atmospheric decoherence, meaning that the amount of time that we can integrate our measurements for is about a factor of 10 times less for ground observing stations than for space observing stations. And so this means that our thermal noise will be worse on our space ground baseline than our space baseline. The solution to this is that you would simply have to integrate for a longer period of time to achieve the same thermal noise floor with the ground telescopes. The ultra-stable oscillator, coming back to one of the questions that was raised, could be the two constraints of less than 1% coherence loss and less than 1 degree phase error could be met by the LISA or JUICE USO. This under development and this with spaceflight heritage. A major problem, question? Okay. A major problem with having a satellite in low Earth orbit performing VLBI is simply the amount of data that your satellite is going to capture. VLBI alone, for example, the EHT, when operating at 230 gigahertz, observing M87 for 6 days, generated about 5 petabytes of data. And so that gives you an order of magnitude for, well, actually, you don't need an order of magnitude. There you go. Our data